Hi everyone, welcome to our third lecture. This lecture is on 1D kinematics, but under the assumption of constant acceleration. This is sort of a joint lecture between both the calc and the non-calc students. The calc students will see a section with some calculus in it, but I'll edit that out of the video for the non-calc students. Okay, the reason I'm doing it this way is so that we get some uniformity over the topics that we're covering in both sections, with the calc students getting the extra calculus that's required for their course. Okay, so last lecture, I introduced general 1D kinematics, okay? And what that means is that, the word general there, what that means is that we really didn't specify any particular assumptions of what kind of motion you had. It could be anything. It could be as complicated, the motion could be as complicated as you want. The only assumption was that it's in one dimension, okay? But that kind of a kinematics, general kinematics, is very difficult to do. It's quite open, and you can't do it correctly without calculus. And even with calculus, it could be extremely difficult because it requires a lot of very complicated mathematics. In this lecture, we're going to narrow down our kinematics and look at just the situation of constant acceleration. Okay, now there's two reasons to do that. The first reason I already alluded to is the fact that the math is much easier. Okay, and the second reason is that this is a very typical situation. All right, so the most common situation where you see constant acceleration is when objects fall. So when you let go of an object and it falls to the ground, it actually accelerates. Now there is air friction, which does modify that, but when you're not talking about getting up to speeds of about 200 kilometers an hour, where air friction really becomes critical, just at sort of like regular speeds, falling, as the object falls, it pretty much falls with constant acceleration. Okay, and this was actually discovered by Galileo in his experiments, where he just dropped things from the top of buildings at the Tower of Pisa, and he discovered that as things fall, they fall with a constant acceleration. So just to remind you, acceleration doesn't mean how fast you're going; it means how fast you're speeding up. And the acceleration due to gravity in MKS units is actually right here. A is equal to negative 9.8 meters per second squared. Now the negative is going to mean down. I'm going to show you how to set up the rulers, the coordinate system for the problems when we do the problems. And if we choose up as the positive direction, well, things don't fall up, they fall down. And so that's what this negative sign means. The 9.8, that's something you can measure. And in fact, you will measure in one of your labs. And of course, the units for acceleration in MKS are meters per second squared. Okay, now that is the number that you should use in any experiments and so on. But in the theory, in other words, in the lecture, we're actually just going to round that off. And it's not that illegitimate to do that. We're going to round it off to negative 10 meters per second squared. So when I do the problems, and even on the test, we're actually going to use negative 10 meters per second squared. Is it off? Yeah, it's off by 2%, which is not that good if you're doing an experiment. You really should do more accurately than that. But it's okay in doing the kinds of problems we're going to do. And there's a great advantage, and that is 10 is a very easy number to work with, whereas 9.8 isn't. Okay, and so when we do some of the math, especially when we get the quadratic equation, which you'll see later, working with an acceleration of negative 10 meters per second squared is a lot easier than working with 9.8. Okay, so that's the assumption that or the number that we'll use for the acceleration due to gravity. Okay, so under the assumption of constant acceleration, okay, which means that A doesn't change over time, it's just some number like negative 10 meters per second squared, the kinematic equations that I gave you last time change, or they simplify. It's not that they change, they actually simplify, and they look like this. Okay, there's three of them that you need to know. And let me just move my image down here so that I don't cover up the numbers on the side here. Here's the first kinematic equation. We're actually going to call it equation number 1. And when I solve problems later on, I'm going to refer to equation 1, equation 2, and equation 3. Okay, and here's equation number 1. All right, so remember, all of your kinematic information is in this position function. So here it is. This is x, the position, as a function of time. Okay, and this can be derived from that. All right, so here's your velocity as a function of time. And then there's the third equation. And this third equation isn't a unique equation. It's actually obtained from the other two equations by eliminating time between them. Okay, so technically speaking, you don't need the third equation. You definitely need number 1 and 2. But when you're solving these problems, it becomes very difficult to do them, or it becomes not very difficult, but increasingly difficult if you don't have that third equation. So it's good to memorize all 3 equations, okay? Because sometimes you'll go directly to equation number 3. Also, later on in the course, when we get to energy, equation number 3 is going to become important. So now is the time to introduce it. But again, it's not a unique equation. It's just like if you take equation 1 and equation 2 and you eliminate the time between them, like solve for time in this one and plug into that one, you get equation 3. Having said that, here we have position as a function of time, velocity as a function of time. And you say, where's the acceleration as a function of time? You don't need it because, remember, acceleration is constant. Okay, so let's look at the form of these equations. So the position as a function of time is actually going to equal 1/2 at squared plus v naught t plus x naught. Okay, like that. All right, so what are all the symbols in there? Well, 1/2 constant. A, there's your acceleration. That's just a number. That doesn't change over time. So when we're doing things that are falling, that'll be like our negative 10 meters per second squared. We won't just do falling. We'll do at least one example where, you know, a car is going along the road and then it brakes. That's a deceleration. But there are lots of examples, okay? So, but, you know, for falling, that number, the A there, would just be replaced with negative 10 meters per second squared. T, of course, is the time. Okay, and so, you know, you're going to look at where the position is at various points in time. Whatever time, say 1 second, 2 seconds, 3 seconds, you plug in that right in there. Okay, and then you've got this V naught and X naught, and you go, what are they? What's this V naught and X naught? And this is just a convenient way of writing the initial position. So the little naught there, the little subscript 0, just means the initial position, and this is the initial velocity. Okay, technically speaking, it's just these quantities here. It's x evaluated at time 0, okay, and v evaluated at time 0, okay. So it's very it's common to write this as x naught and v naught. So x is like the position at time t, v is the position at time t, x naught is the initial position, or the position at t equals 0, okay, and v naught is the initial velocity, or the velocity at t equals 0. All right, let's look at those equations again. Okay, so over here we have the position at some later time t is equal to 1/2 at squared plus v naught t plus x naught. Okay, and again, this is the initial position and that's the initial velocity. All right, what about the velocity as a function of time? So the velocity as a function of time is just equal to a times t plus v naught. Okay, so there's an initial velocity there plus a t, like that. And then finally, the third equation, like I said, you just eliminate time between these two. Okay, in other words, when I say eliminate time, I mean like you isolate time in this one and plug it into that one. Then you crunch through a bunch of arithmetic, which I'm not going to do for you, a bunch of algebra that I'm not going to do for you, and you get this equation here. Okay, and this v here, that's actually v of t. All right, I just took out the t to make it read a little bit better, And so the velocity here squared at a later time, so the velocity at a later time squared is equal to the initial velocity squared plus 2 times a, the acceleration, multiplied by x minus x naught. Okay, so that's the final position minus the initial position. All right, and you just heard me call this a final position. Oftentimes when you're doing these problems, especially if you're reading some other textbooks, they may not write this as x or call this x of t or the position at time t. They'll sometimes call it the final position. So they'll say this is the initial position and this is the final position. And the image there is that, you know, this object is moving from some initial to some final position in time t, like that. It'll all become clearer when we do some problems. Okay, so here are our 3 equations, and they are worth memorizing because when it comes to a test, the last thing you want to do is fumble around with these equations. Okay, so there they are. All right, and there's the explanation of the symbols. And the last one, a, acceleration, as I said, it's a constant. It doesn't change over time. All right. Now, to really understand what those equations are saying, it's worth looking at their graphs. Okay, so let's start off with equation number 1. That's the one that says x is equal to 1/2 at squared plus v naught t plus x naught. What does it look like? Well, you know that any function which has a square in it, where the independent variable has a square, so it's a t squared, what does it look like when you graph it? It's a parabola. So here it is. So remember, we plot the position on the vertical axis and the time on the horizontal axis. So let me just scroll that up just a little bit here like that. All right, so you could see here, here's the time on the horizontal axis and x on the vertical axis there like that. And if you were to plot that function, what would it look like? Well, if you put t equals 0 in there, that is, where are you at t equals 0? Well, then the 1/2 at squared, that's just 0 because t is 0, and so t squared is 0. Okay, plus v naught t, well, v naught is 0, and all you're left with is x naught, and that's exactly what you expect, because where is the thing at t equals 0? At its initial position. So if you were to start the graph, it'd be right here at t equals 0. There you go. There's x naught. That dot right there is x naught. All right. And now you got plus v naught, and then you also got plus 1/2 at squared. And what does that look like? It's parabolic, like this. Okay. Now the parabola can either frown, like it can either curve this way, the way you're seeing it in the graph, or it can smile. All right, and that all depends on the sign of A. So if A is negative, like it is for falling, then the parabola curves downwards like this. Okay, if A were positive, it would curve upwards. Okay, so because I'm thinking about the situation where you're falling, I put A negative in this graph, and so here it is, A is curves down like that. All right, now remember, so that's it for the position. Let's move on to the velocity. Now remember that to get the velocity from the position, because that was kind of the subject of last class, okay, and to get that velocity out of the position, what you could do is you could just look at the slope of this graph here, okay, and the slope of this graph is the velocity. So let's take a look here at what the slope looks like. So let me just try to scroll down a little bit like that. Okay, and this is good enough. So if you take a look here at x naught, you say, what is the slope? Well, the slope is positive there, like that. Okay, and what is the value of that slope? That is v naught. That's exactly what v naught is. V naught is the slope at this point right there. And you can see that since it's sloping upwards, that the slope here is positive. And so here you go. At t equals 0, you have a positive slope in this graph. And so your v naught is positive. All right. Now, over here, as this goes up, it eventually gets to the top of the parabola like that, okay? Now, if you ask, what is the slope at the top of the parabola there? The slope of the top of the parabola, remember, you could get the slope, which is the instantaneous velocity, by the tangent line. If you were to draw a tangent line here, which I didn't do to just not to clutter the diagram, but you could see that if you put a tangent line there, it would be absolutely horizontal. Now, a horizontal line, what's the slope of a horizontal line? 0. So at the very top of the parabola there, your velocity is 0. Why? Because the slope is 0 there, so the velocity is 0 there. Okay, so you go from a positive slope here to 0 slope. You go from a positive slope there to a 0 slope there. And then as you start to come along the other side of the parabola, your slope becomes more and more negative. Okay, because if you're sloping down this way, then you've got a negative slope in there, and it becomes increasingly negative. Okay, in other words, it becomes steeper and steeper and steeper. And so the velocity as a function of time looks like this. Okay, it's actually a straight line, and you can see that from the equation. Let's go back up to the equation so we can see how those graphs are coming out of the equations. So we're really just concentrating on equation 1 and equation 2. Equation 1 is the equation of a parabola, which we just saw. Okay, equation 2, we'll take a look. It's just like, remember what the equation of a straight line is? The way you usually learn it in math is y is equal to mx plus b. But it's the same thing here, but all the names have changed. So it's not y, in this case v, okay, mx, but instead of x we have t, and the slope is a, all right, and then plus x naught, okay. So this is the this is an equation of a straight line here like that, okay. And so there we go. There's the velocity graphed, and it's actually a straight line like that, okay. And then finally, how do you get the acceleration out of the velocity? The acceleration is the slope of a velocity graph. Well, that's really trivial in this case, because why? Well, because the slope of the velocity graph is constant negative. Like the slope is the same everywhere along here. So it's constant and it's negative. So guess what? Of course, you're going to get just a constant negative number here like that. Okay, so A is flat, because the slope here is constant, all right? And it's negative because, well, it's sloping downwards like that, and so it's actually negative, all right? It's a negative slope. And the fact that it's flat means that a doesn't change over time, and that's our original assumption. Our original assumption was exactly that, that we had constant acceleration. And so you can see that those three equations give rise to these three graphs that I just showed you, and the critical assumption that a doesn't change over time, that it's constant, is you can see in the final graph right there. Okay, so there's nothing more to really say about this. Next, what we can do is just start to do some problems. Most of the course is going to actually be about solving problems. This particular section of the course that is introducing the kinematics has a lot of theory. So if you feel overwhelmed with theory, don't worry about it. I mean, it was important to get you to the point where we can do these problems. But now, you know, for the remainder of this lecture and then into the future, we're just going to be solving problems. Okay, so here's my first example. All right, we have a car traveling at 50 kilometers per hour. Remember, that's roughly, you know, the speed that you travel in a city, the 30 miles an hour. Okay, so we have a car traveling at 50 kilometers per hour along a straight road. Okay, and the driver hits the brakes, and the car comes to a halt in 100 meters. Okay, so, you know, most people have had to do this. You hit the brakes and you come to a complete halt. All right, so two questions: how long did it take the car to come to a stop? That's question number one. And question number two is, what was the acceleration? All right, so this is a pretty easy problem, and if you know how to do these problems, fine. But I would recommend that you follow the steps that I just tell you, because as these problems become more and more difficult, you'll discover that if you skip some of the steps, you'll probably make mistakes. Okay, and you'll make mistakes because you'll have those equations. You'll just start plugging numbers into those equations, and you'll plug the wrong numbers in, and that's because you didn't think carefully about what the initial position, the final position, the initial velocity, and final velocity are. And so I recommend that you do these problems as I show you. All right. So here's how you start. The first thing you do is just draw a picture. Don't worry about the ruler or anything like that. Just draw a picture. So before you even put the minus and plus here like that, just draw a line like that. That's the road. And then draw a car here. That's when the car first starts to brake. And then draw the car again. That's where the car stops braking. Okay. Now, the next thing that you're going to do, that's after you just draw a diagram. Don't worry about time. Don't worry about position or anything like that. The next thing you're going to do is you're going to slap on top of that your ruler and your clock. Okay, so that's like as if you were doing an experiment, that you were going to measure things. And so on my road here, okay, I'm going to say, look, this is my positive direction. And I could have even written positive x, okay, like that. This is my negative direction. And then right here, this is the point where the car first starts to stop. I'm going to call that 0. I'm going to call that my origin. All right. And you remember last lecture, that was like where the tree was. But, you know, you could choose your origin any place you like. And you could say, you know what, I'm just going to mark on the road the point at which the car first starts to brake. And that's going to be my 0. Okay. And then the car travels, how far? It travels 100 meters until it stops. Okay. Now, at this point, you could have just written a 0 here, or 0 meters here, and 100 meters there, okay, and you would have been fine. But let's be very precise here about what that 0 and the 100 meters mean. The 0, that's your initial position. So you can see here that I have x naught is equal to 0. That's because when I go to plug into my equation, that's going to be my initial position, okay? And then the car travels some time and then eventually stops. When it stops, the instant at which it stops, that's my final position. And so over here I wrote x is equal to 100 meters. And you can see by doing it this way, it's going to become very clear what numbers to plug into the equation. Okay. And so once again, the steps are just draw the picture. The second thing is draw your ruler on there, and also draw any times that you have. For instance, t equals 0. That's when the car is at the origin. That's when the car first starts to brake. And then t equals question mark. That's when the car comes to a halt. Why did I put question mark there? Because we don't know at the beginning of this problem how long it takes the car to halt. I didn't tell you that. So if you read the problem again, you know, I just say a car is traveling at 50 kilometers per hour along a straight road. The driver hits the brakes and comes to a halt in 100 meters. That's it. Did I tell you anything about time? Nope. And so over here, the final time is equal to question mark. You always get to choose where your origin is. You get to choose where the origin in space is, and you get to choose where the origin in time is, okay? But of course, the later time, like the point at which the car halts, you just don't know that. And so when I do that, I'll put t is equal to question mark. In fact, that's one of the questions. How long does it take to halt? So we'll be solving for that. The other thing are the velocities. And so you could say, okay, there's an initial velocity here. So how fast was it going when I first hit the brakes? Well, you read the problems and it was 50 kilometers per hour. Okay. And how fast is it going when it comes to a halt? Well, it's 0. Okay. So because when you come to a halt, you stop. All right, so that's 0 meters per second. All right, so if you go back to those equations, you take a look at them, you'll see that there's kind of a pattern to all the variables that you have to identify. You have to identify an initial position, an initial velocity. You have to identify a final position, a final velocity, a time for the entire motion, and then the other variable in there is the acceleration. And you say, do I know the acceleration in this case? And the answer is no, you don't. And so I also have a is equal to question mark. All right. So once you've done this, you now have all of the variables identified that are going to go into that equation. Life becomes a lot easier and you're not going to make a mistake. The kinds of mistakes that are made is people will sometimes implicitly, because they don't explicitly draw where the origin is, they'll sometimes say, oh, the origin is here. And then halfway through the problem, they'll move the origin somewhere else. They won't know they did it because they're not thinking clearly about it. They didn't explicitly draw in where the origin was. And then, of course, once you change the origin, the numbers change, and then you get into problems. I'll show you that a little bit later when we do our next problem. So let's just finish off this one. All right. And we look at the numbers here, and you'll see that 0, 100 meters, those are an MKS. But the 50 kilometers per hour is not an MKS, okay? And so the next thing we're going to do is convert all of our numbers to MKS units. So we have here 50 kilometers per hour. We've done this conversion now. This is the third time we're doing it. So remember, we want to eliminate the kilometers and go to meters, and we want to eliminate the hours and go to seconds. And so we multiply by this fraction, which is equal to 1. It's 1,000 meters divided by a kilometer. And we multiply by this fraction, which is also equal to 1. It's 1 hour divided by 3,600 seconds, okay? After you've done this a number of times, you're going to realize very quickly that to convert from kilometers per hour to meters per second, all you have to do is divide by 3.6. Okay, so you don't have to go through all of these steps. Okay, once you understand the steps, why they work, you can develop your own shortcuts, because then you won't make mistakes. It's when you create a shortcut and you don't understand why it works that you're going to make a mistake. So why is dividing by 3.6 work? In other words, like you just take 50 divided by 3.6 and you get 13.9, and that's the answer. And the reason is because you're multiplying by 1,000 and you're dividing by 3,600, and that's effectively the same as dividing by 3.6. Okay, so in the future we could just directly go from 50 kilometers per hour, divide by 3.6, 13.9 meters per second. It gets a lot easier. Okay, so for that V naught, we're not going to plug in 50, we're going to plug in 13.9. Okay, now the next step is, which equation do you want to use? And there's always some choice, because remember that equation 3 was derived from 1 and 2. And so you could do it in different ways. And if you're working on these problems together and you get different answers, or you approach it in a different way but get the same answer, that's fine, and that's to be expected. But if you take a look at the numbers that I have here, so let's look back at my picture here, you'll notice that equations 1 and 2 have the time in them, okay? But we don't know the time, the final time, that is the elapsed time, okay? Like I know there's an origin, that's t equals 0 is the origin, but that's not the t that you want to put into the equations, it's this t. It's like how long did the process take, did the motion take, okay? But we don't know it, so that immediately eliminates equations 1 and 2 as a possible way of approaching this. And so equation 3 is the way to go. Okay, so it's pretty easy. It doesn't take a lot of playing around. You've only got 3 equations. You could say, well, do I use equation 1? Do I use equation 2? Do I use equation 3? And then after just doing a few problems, it becomes obvious which one of the 3 equations is the easiest way to go. So again, it's not impossible to do it the other way. It's just that if you do it one way, you're going to get two unknowns in equation 1, and you go, well, what do I do with that? Well, then you can use equation 2 and you'll get 2 unknowns. And then you eliminate one of the unknowns between the two, and guess what? That is equation 3. So it's pretty obvious that we should use equation 3. There it is. And now, because we were very careful about identifying the numbers from our picture, we know that the final velocity is, from the picture, 0. That's because it stopped. Okay, we know that the initial velocity was 13.9 meters per second. We don't have to write the units into the equations. So when we plug into the equations, you don't need the units. Why? Because all of the units are MKS. And remember what I said? The answer will come out in MKS. Okay. And then we have 2 times A. We don't know A. Okay, the acceleration. The final position is 100 meters. The initial position was 0. And so we have this equation here with the number substituted in. The next line is just some arithmetic. Okay, and then just solve for A. In other words, how would you do it? Subtract 193 from both sides, then divide by 200, and you're going to get that A is equal to negative 0.96. And now we can put the units back in, and we know they're MKS units. So what are the MKS units of acceleration? Meters per second squared. So the answer for the acceleration is not negative 0.96 meters per second squared. Okay. Now, when you get an answer, don't just write it down or whatever. All right. Think about whether the answer makes sense. Now, right now, you don't have a good feeling for how big acceleration is, but you do a little bit because you know that the acceleration due to gravity is 10, and 0.96, that's close to 1. And is it reasonable that when you're stopping your car, you're decelerating at about 1/10 the acceleration due to gravity? Yeah. Okay. Imagine if you were doing this and you got an answer which was 100 times the acceleration due to gravity. Well, that can't be. Why? Well, because if you decelerated at 100 times the acceleration due to gravity, that's unphysical. You'd be squished in your car, okay? That would be like stopping almost instantly. And so when you got these numbers, try to compare them to some other number that you know you have a physical feeling for. And 1/10 the acceleration due to gravity is about reasonable. In fact, like in jets, okay, if you get up to 7g, which is 7 times the acceleration due to gravity, you're pretty close to fainting. Okay, maybe 9g for a little bit, but like your body can't handle too many g's. So if you have a car and it's stopping, and unless I make a mistake and put in some really weird numbers, but these are not weird numbers, okay? 100 meters is like 300 feet. 50 kilometers per hour is 30 miles an hour. Can you stop your car when you're traveling 30 miles an hour? Can you stop in 300 feet? Yeah, that's pretty reasonable. You can do that. And so you expect a reasonable number to come out here. And 1/10 the acceleration due to gravity is reasonable, okay? 100 times, if you by accident got like 100 times the acceleration due to gravity, well, that can't be, because you wouldn't even be able to survive 10g, never mind 100g. Okay, so always look at the numbers that you get as an answer and just ask yourself, interpret them and say, does this make physical sense? Okay, so the magnitude here, that's just a number without the direction at 0.96. Yeah, that kind of makes sense. Yeah, it's about 10th the acceleration due to gravity. And what about the negative? Well, let's take a look at the diagram again. The negative here is because the car is moving to the right, but it's slowing down. So it's starting off with a big velocity and it's going down to a zero velocity. So the acceleration is always to the left, to the negative side. Okay. In other words, the acceleration is such that it is pulling the car, or changing the velocity in the negative direction. All right. So yeah, the negative sign does make sense here, okay? And just to be very clear about these words, acceleration and deceleration, usually we say decelerate when you're slowing down. So when your velocity is in one direction and the acceleration is in the opposite direction, what does that mean? It means the velocity is going to decrease over time, and that's what we mean by deceleration. So over here, the fact that the velocity is in the positive direction, whoops, I went too far. The fact that the velocity is in the positive direction, but the acceleration is in the negative direction, is exactly what you expect as your car decelerates. Okay, so that answers one of the questions, which was here are the two questions. I'm not doing them in the order that I asked them. So we actually answered part B first. What was the acceleration? And the other one was how long does it take the car to come to a halt? In other words, let's solve for t. And for t, you could just take a look at the equations. We have a now. We have a, and it's pretty obvious that equation number 2 is the easier one to use. And so we have v is equal to at plus v naught. And you say, do I know all those numbers? Yeah, everything except for t, which is what you're solving for. So the final velocity is 0. Okay, the acceleration, we just found that is negative 0.96. All right, t is what we're solving for, plus v naught, which is 13.9. And there it is. And how would you do the arithmetic? Well, you could subtract 13.9 from both sides and then divide by negative 0.96, and you're going to get 14.4 seconds. Okay, and so basically it would take this car 14.4 seconds to come to a halt. Okay, so again, you're traveling 50 kilometers per hour and you're stopping in 100 meters. 14.4 seconds, yeah, that kind of makes sense. That kind of makes sense. Or maybe in units that you're more familiar with, even though we're not going to use the usual American units like miles per hour. But you have a good intuition, miles per hour. If you're going 30 miles per hour and you want to stop in 300 feet, how long would it take? 15 seconds? That makes sense. Now, again, look at the number. And if you got 3 hours here, like 9,000 seconds or something, well, that's crazy, because that's not just going to happen. Or if you got something like 0.01 seconds, well, you're not going to stop in a hundredth of a second. So, just think about it and see if the answer makes sense. And it doesn't. That is the correct answer. Okay, so that's it for that first problem. It was a really easy problem, and it was mostly to show you the steps that you take in order to solve these problems. Okay, when you get really good at it, you can almost jump in and solve them right away. But I recommend that you follow the steps that I just mentioned, and that is, first draw the diagram without the ruler, without a clock or anything like that. The second thing, and choose an origin and draw in your ruler. Okay, and also choose your time. So there's a place where the thing is at t equals 0, and there's a place where it is at a later time. All right, and then start to read off. It's almost like you're doing an experiment. Let's go back to the diagram for a second here. It's almost like you're reading off the ruler. Where is the car here? It's at x equals 0. And that's what? That's your x naught, your initial position. And then you read off of the ruler here. Where is it here? It's at 100. That's your final position. That's after you come to a halt. And then, this is a picture, not a movie, but, how fast is the car moving here? It's going at 50 kilometers per hour over here. So that's your v naught, your initial velocity is 50 kilometers per hour. And then how fast is the car going there? Well, it stopped. So v is equal to 0 meters per second. And what was the time there? 0. And what's the time there? Well, we don't know, but that's the later time. Okay. And then what's the acceleration? We don't know, but there is an acceleration between these 2 points. And so there it is. And now once you've identified all of the variables, then you can start thinking about which equation you're going to use. You may have to convert, obviously, but you can think about which equations to use. Plug into the equations in MKS, and out will come the answer in MKS. Okay? All right, so there was our first problem. Let's do another problem, which, move my image up here. Let's do another problem which is less trivial. Okay, so this is more demanding. And we started off the lecture by saying that the acceleration due to gravity is 9.8 meters per second squared, rounding that off to negative 10 meters per second squared. And so this first problem is going to show you how things fall. Okay, so here I am. I'm at the top of a building. This little image right here is a little stick figure of, say, me standing at the top of a building. And what I'm going to do, the building is 30 meters high, like that. What I'm going to do is I'm going to throw a ball straight up. Okay, so I'm throwing, because this is all 1D motion, everything has to be along a line. Even if it goes up and down, it has to be along a line. We'll do 2D, which is like, going along some kind of a trajectory, but that we're not ready for that yet. So I throw the ball straight up, and I throw it straight up with an initial velocity of 25 meters per second, okay? So that's the situation that I'm setting up for you. Let me just say it again. I'm on top of a building which is 30 meters high. Okay, so I'm at the top of this building, 30 meters high. There I am. I throw a ball straight up. There is the ball going up. The initial velocity is 25 meters per second, okay? Now, I didn't ask any questions yet. I'm just setting it up, all right? So the first question I'm going to ask is, how high does the ball go? How high does the ball go? So remember, when you do this, when you do these problems, the first thing is just draw the diagram. So draw the building, draw the person at the top of the building, draw the ball, okay? And maybe you could draw the trajectory of the ball, like going up and coming back down like that, all right? And that's fine for the first step. The second step is put a ruler there, and maybe even a clock. I don't have the clock right now, but you definitely need the ruler. And here's where the question of the origin becomes very important. Remember I said a minute ago, people, when they just jump into these problems and they don't actually draw in the ruler, they'll move the origin all over the place. Because if I ask you, where do you want to put the origin? there's two kind of answers where you can put it. You could actually put it anywhere you like. You could put the origin here. You could put it up there. It probably makes sense to put the origin at the base of the building, like at ground level here, like that. You don't have to, though. You could put the origin at the top of the building, okay? And if you did that, and you have a friend that puts the origin down here, and you put the origin there, and you solve the problems, you'll both get different numbers. But that's okay, because the different numbers will actually correspond to the same answer, because when you go, the person who put the origin there would say, well, that, at 0, it's at the top of the building. But the other person who put the origin down there would say, oh, it's at the top of the building, it's 30 meters. But you see, it's still both at the top of the building. It's just because you move the origin around that you got different numbers. But when you go to interpret those numbers with the ruler, the way you placed it down, you'll actually get the same point in space, okay? And so moving the origin around can change the numbers on you, all right? But it won't change the actual final answer, okay? So now the next step is let's put the coordinate system in. We're going to choose the origin down here. If the origin is there, then the top of the building up there is 30 meters, okay? And of course, when I throw the ball up, it goes up further and comes back down like that, okay? Further than 30 meters, all right? So how high does the ball go? All right, now we can start to answer it. Let's read off the numbers from the diagram. So you might do this very systematically, and let me scroll down for you a little bit here. You might go systematically and say initial position, final position, initial velocity, final velocity, acceleration, and time. Okay, so we'll try to just follow this pattern. Initial position, where does the ball start? Well, we've got to scroll back up to the diagram here. The ball starts off at this height right here, which is 30 meters. So x naught, the initial position, is 30 meters. Okay, where does the ball end up? It ends up here. Okay, and how high is that? Well, that's x, the final position, but I don't know how high that is. Okay, so question mark like that. All right, and in fact, that's what I'm asking for. I'm asking for to solve for x and x. Okay, the final position. So it starts here, it ends here. I know it continues past the highest point, but as far as the motion that we're concerned about, we're just concerned about the motion from there to up there. Okay, so it starts at x naught equals 30. It ends up at x, which is, I don't know, bigger than 30, but I don't know what. Okay, and then we can go to the initial and final velocity. Let me just scroll down a little bit here. The initial velocity is, well, I told you, it's 25 meters per second. I put the plus in there to be very explicit. Plus because it's up, okay? Now, you don't have to put positive up, but I recommend, so that we're all on the same page, that when we do these problems where things are falling, that you make up positive and down negative, okay? And so if I throw the ball up is positive, it's positive 25 meters per second, okay? And when the ball gets to the very top, ask yourself, how fast is the ball going at the very top? And the answer is 0. Why? Because when you're going up and you get to the very top, that instant when you're at the very top, your velocity goes to 0. See, as you're going up, your velocity is positive. As you're coming down, the velocity is negative. Where does the ball stop going up and start going down? That's at the very top. That's when the velocity changes from positive to negative, and that's where the 0 is. Okay? Now, let's go back just for an instant to the graphs I gave you earlier on. Okay? And so there were these two graphs here like this. And here was the position as a function of time. This actually is my problem. Now, I know that the time is along the bottom axis here, but we're just measuring x, how high you are. You start at the top of the building, you go to your maximum height, and then you come back down again. Okay, and so over here, there's your maximum height. Well, what's the slope at the very top? Well, the slope at the very top is 0. That's your 0 velocity. So here's your velocity as you go up. That's where you stop at the very top, and there's your velocity as you come back down. Okay, now as you go up, the ball's going faster, and then it goes slower, 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 until it gets to the very top. The velocity is 0, and then it starts to come down. At first it comes down slower, and then it goes faster and faster and faster down. So the velocity is negative now, but becoming more and more negative. Okay, and so you can see that these two graphs actually correspond to the problem that we're working on right now. Okay, and so Oops, scroll down a little bit more here. Okay, and so what we have here is an initial velocity of 25 meters per second. And when we get to the very top, okay, that's because we're asking how high does the ball go. We're talking about the highest point, and at the highest point the velocity is 0. Okay, so the final velocity is 0. The acceleration, do we know it? Yeah, it's gravity. Okay, so if this were the lab, we really should use negative 9.8 meters per second squared. But like I said in the lecture here, we'll do negative 10 meters per second squared. And how long did it take to go from the where I throw it to the very top? We don't know, and so that's a question mark too. Okay, and so you'll see that you can even just like sort of memorize this chart here: initial, final position, initial, final velocity, acceleration, time, and you just go through them. And after you've put down your ruler, you just measure them off. 30 meters, unknown. 25 meters per second, up, 0. The acceleration, because we're on Earth, okay, and the acceleration due to gravity at the Earth's surface is a fixed number. You can put in negative 10 meters per second squared. And the time you don't know. You just fill in that chart, and now you're ready to start plugging into the equations. If you followed my steps, you'll almost never make an error, okay? It's very hard at this point to make an error. It's very easy if you just skip the step where like you just jump to like plugging in the numbers into the equation. You could very easily like accidentally put in 0 here for the initial position, and then everything gets messed up. Okay, so all right, there we are. Let's solve the problem. And you say, well, which equation should I use? Well, scroll too far here. Which equation should I use? And you'll see that since you don't know the time, just like in the previous problem, when you don't know the time, it's probably best to go to equation number 3. So equation number 3 is v squared plus v naught squared plus 2ax minus x naught. Substitute in the numbers. Your final velocity is 0 at the very top. Your initial velocity is 25 squared plus 2 times negative 10. There's your acceleration due to gravity. X minus x naught, we don't know how high it is, but that's what we're solving for actually, and then minus 30. And you'll see that once you substitute in all the numbers, the only unknown variable is x, and then you can solve for that. Okay, and it turns out to be 61 meters. Okay, and so back to the diagram here. If you ask how high is this point, measuring from the ground, because that's our x equals 0, all the way up to here, that's 61 meters. That's 61 meters. And not to belabor the point, but if someone else does this problem, and you might want to try it later yourself, and you put the origin here, you know what you're going to get as an answer? 31 meters. Why? Because the distance from there to there is 31 meters. If the distance from there, from the ground to there, to the top there, is 61 meters, then from the top of the building to the highest point is 31 meters. Okay, so moving the origin around will change that number, x, but when you go to point to that point in the diagram, okay, you'll see that it actually corresponds to the same point up there. Okay, so great. That answers our first question: how high did the ball go? And the answer is 61 meters. Okay, next question: how long did it let me move this down here. How long did it take to reach its maximum height? In other words, now I want to know the time that it took to get up there. Okay, and we don't have to redo all of the variables because we've kind of solved them already. We've already identified the variables, so you don't have to redo that step, the step right in here. Okay, you don't have to redo that step. We can just use it again for the next one. And so what is the maximum, how long does it take to reach the maximum height? Well, you can go through the equations and you'll notice that equation number 2, you could easily solve time in that one. And so the velocity at the maximum height is 0. The acceleration negative 10 times t plus 25, and you get an answer of 2.5 seconds. Okay, and so if you look at the diagram here, starting from this point right here and going up to the very top takes 2.5 seconds. So you're here at t equals 0, and then tick, 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 like 1 second, and then 2 seconds, and then 2.5 seconds. You're at the very top. Okay. So let's move on to the next problem. Okay. Now I'm going to change things up a little bit. I'm asking you, how fast is the ball going when it passes you on the way down? Okay, so I know the ball is going to continue going all the way down to the bottom, but I just want the motion from when I took the ball, threw it up into the air, and had it come back down, and it passes me on the way back down. Okay. Well, if have a good physical intuition, you might be able to guess the answer right away. And the intuition is that the motion on the way up is symmetrical with the motion on the way down. Okay, so on the way up, let's think about what happened here. You start off at 25 meters per second, and then you slow down 20, 15, 10, all the way down to 0 at the very top. So you start at 25 and you get down to 0 there. Well, guess what happens on the way down? It's the same thing, but the other way around. So up here, you're going to have 0, and by the time it passes you on the way down, it's going to be 25. But it's moving down, so the answer, you could almost just intuitively guess, is going to be negative 25 meters per second. Okay, so there you go. Spoiler alert. On the way back down, when it passes you on the way back down, it's going to be negative 25 meters per second. But let's do that using the equations, because answering it using the equation gives you a little bit more intuition into how those equations work when the motion is symmetrical around the maximum point of the parabola, which is right up here. Okay, and so let's start over. In other words, let's start measuring those variables all over again. And the reason we're going to do that is because now the final position is different. The initial position is still 30 meters because I'm still throwing it from the top of the building, but the final position isn't up here now. Now the final position is back where I'm at. In other words, 30 meters again. So it starts at 30 meters, does its motion, and it ends up at 30 meters again. Notice that that's different than before. Before we had starts at 30 meters and gets up to an unknown height. Here it starts at 30 meters, goes up and comes back down to 30 meters again. Okay, so that's why we have to redo this. Like if you change the problem, if I change the words, I'm asking for a different portion of the motion, you might have to rethink those variables. So it's always good to go back and redo all the steps, okay? So, all right, initial position, 30 meters, final position, 30 meters, initial velocity, 25 meters per second. Final velocity, I put question mark here. We know intuitively it's going to be negative 25, but let's see that coming out of the equation, okay? And A is going to be negative 10 meters per second squared, and then the time is also unknown. You can almost guess what the time is going to be too. And the reason is, if it takes 2.5 seconds to go up, guess how long it takes to come back down? 2.5 seconds. So 2.5 seconds plus 2.5 seconds, 5 seconds. So t here will actually turn out to be 5 seconds. We'll see that in a minute. Okay. Now you take a look at this and you go, well, which equation do I want to use? All right. Well, you know what? I mean, you could try several different things. You could use equation 3 and so on. But you know what? Let's start off by using actually equation 1. All right, so let's use equation 1. Equation 1 is the harder one to work with because it's actually a quadratic. But in this particular case, it's an easy quadratic to work with. All right, so we use equation number 1, and here's equation number 1, just rewritten verbatim from above. X is equal to 1/2 at squared plus v naught t plus x naught. Okay, so there's equation number 1. Let's substitute in the numbers. So for the final position, it's 30. The acceleration was negative 10, so for A we put in negative 10. The initial velocity was plus 25, so there it is there. And the initial position is 30. So this is the final position is 30, and the initial position is 30 there, like that. Okay. All right. So now you'll see that 30 on both sides of the equation just drops out, and if you take 1/2 times negative 10. That's equal to negative 5t squared. So this first term is negative 5t squared plus 25t. This line here reduces very nicely to 0 is equal to negative 5t squared plus 25t. Okay. Now to make life very easy, we could just solve this. We don't need the quadratic equation. We will need it in a minute, but not yet. So we could just take the negative 5t squared to the other side. So we get 5t squared is equal to 25t, like that. And then we have t squared is equal to 5t. Now you got to watch it. This looks like it has only one solution, but it actually has two solutions. There are two possible numbers that you can put in for t that solves this. Okay, and let me let me move my image up here. Okay, one solution that works in here is t equals 0, because if you have 0 squared, the left-hand side is 0, and if you have 5 times 0, that's also 0. So one solution is t equals 0. The other solution is if you divide both sides by t, is t equals to 5 seconds. Okay, so the answer we do want actually is the 5 seconds, but there is a meaning to the t equals 0, because you know what you're actually asking. with this equation here. You're asking at what times is it at 30 meters height? And the answer is it's at that height twice. Let's go back to the diagram here so we can understand it. Here we are at t equals 0. How high are you? 30 meters. So at t equals 0, you're at 30 meters height. And then you're not at 30 meters height. You're not. And then at 5 seconds, you're at 30 meters height again. And so that quadratic equation, all quadratics have two solutions. So there's two solutions for the time here. You just have to make sure that you interpret those two solutions. In our case here, the two solutions are t equals 0 seconds and t equals 5 seconds. And do we have an interpretation for both of them? Yes. It's at 30 meters at t equals 0 seconds, and then it's at 30 meters again at t equals 5 seconds. Okay, so the way I worded the question, though, we want the 5 seconds because I want to know how long does it take before it goes up and down. So I assume that it already went up before it came down. But if you just strictly ask the question, at what times, like on the clock, when would you see the ball at 30 meters height? You would see the ball at 30 meters height when the clock reads 0 seconds, and you would see the ball at 30 meters height when the clock reads 5 seconds. Okay, so that's why there are two solutions here. All right, now that didn't quite answer the question. The question was, how fast is the ball going? But once I've got the time, I can substitute that into equation 2. And so once I put it into equation 2, the final time is equal to a times t plus v naught. And a is negative 10. T we just identified, or just solved, was 5 plus 25. So we get minus 50 plus 25, and that's negative 25, which is what we guessed a minute ago. Okay, and so when the ball comes back down and it's passing me on the way back down, it's actually traveling 25 meters per second, negative downwards. Okay, what if we had put t equals 0 in there? That's the initial time. Well, if you put t equals 0 in there, you wouldn't have 5 there. You would have 0. The first term would disappear, and you would just get positive 25. That's right. Initially, at t equals 0, the ball is moving up at 25 meters per second. 5 seconds later, when it passes by me again on the way down, it's traveling negative 25 meters per second, 25 meters per second down. Okay, so this is trying to show you, this problem here is trying to show you that there is a symmetry in these problems between going up and going down. Okay, and that symmetry is actually evident in those graphs that I gave you earlier. So let's scroll back up to the graphs. Okay, if you take a look at the graph here, there's a parabola. The parabola has a symmetry right along that dashed line. By symmetry, I mean, this side of the parabola looks the same as that side of the parabola. If you put a mirror over here, like right along the dashed line, this side would map onto the other side and vice versa. Okay, so there's that symmetry. All right, so at 30 meters here, if the slope right here is 25, that is, the velocity is the slope. If the slope here is 25, well then guess what the slope is right there? Negative 25, which is exactly what we saw. And so equation number 1 really is the equation of this parabola. So now I gave you an interpretation two different ways. One in terms of the quadratic and another in terms of the parabola. Okay, let's continue with the problem. And so the next part of the problem, oh, sorry, before we continue with the next part, let me show you yet an alternative way to solve for the velocity on the way back down. You could have just used equation number 3 to start with, okay? And you might have guessed that because you say, well, I don't know the time, and you've been saying if you don't know the time, use equation number 3. I used equation number 1 on purpose to show you that quadratic and the symmetry, okay? But if you'd use equation number 3, you would still get two solutions, okay? And you say, well, how does that happen? Well, here we go. Here's equation number 3. V squared is equal to v naught squared plus 2ax minus x naught. When you substitute in the numbers, you get v squared is equal to 25 squared plus 2 times negative 10, 30 minus 30. The 30 minus 30, that's 0. So this entire second term here, that entire second term is 0. So you just wind up getting that v squared is equal to 625. When you take the square root of that, you got to watch it. Whenever you have a square, there are two possible solutions. And the two solutions are negative 25 and positive 25. The positive 25 is obvious. You can just do this on your calculator. You do 25 times 25, you're going to have 625. But the negative also works, because if you do negative 25 times negative 25, a negative times a negative is a positive, the negative sign disappears. And so even if you use the equation number 3, you get two solutions, and you have to interpret them. Well, we know what the interpretation is. The plus 25 meters per second, that's when you're on the way up, and the minus 25 meters per second, that's when you're on the way down. Okay, so I just wanted to show you this before I move on to the next section, because all of the equations, they give you the same interpretations. I mean, they might get there by different steps, but you know, they're really giving you the same interpretation. And you have to watch out, because equation 1 and even equation number 3, there are 2 solutions in there, okay? And the reason they're coming in there is because of square. Whenever you got a square in an equation, you're solving for it. Implicitly, it's a quadratic, and all quadratics have 2 solutions, okay? So there you go. There's the 2 solutions using equation number 3. All right. Now, let's look at this problem one more time, okay? And let me move my image down here. How long does it take before the ball hits the ground? Okay, and now everything has been turned around. All right, so or been changed. Now we no longer can make use of the symmetry. We start up here. We don't end up here at the same point. We end up at the bottom. I know that this portion of the parabola is symmetrical, but not the whole length. Okay, this extra bit is not symmetry. There's no equivalent of that on the other side. Okay, so in situations where you have, you know, the motion and it's parabolic motion like this, but it's not symmetrical, okay, where it doesn't like end where it began, well then there's no way you can do it as simply as you can before. Unfortunately, we're going to have to make use of the quadratic formula, as we'll see in a minute. Okay, so I didn't go through and rewrite all of the variables again, because the only one variable changes, and that's your x, okay, your final position. So the initial position is still 30. Okay, we're going to use equation number 1 to solve this. Your initial position is still 30. Your initial velocity is still 25. Your acceleration is still -10. You're solving for t because that's what I asked for, how long. So there's t. But now the final position isn't 30. The final position now is 0. Okay, why? Because it gets all the way down to ground level. Okay, and so x is equal to 1/2 at squared plus v naught t plus x naught. Substituting in gives you 0 is equal to 1/2 times -10t squared plus 25t plus 30. Okay, the rest of it is just some algebra, and I'll go through that very quickly. So, you know, 1/2 times -10 is -5, and then what I'm going to do is just bring everything to the other side so that the -5t squared becomes positive t squared, the plus 25t becomes -25t, and the plus 30 becomes -30, like that. And I like to always divide by the coefficient here, 5. And so I'm going to divide everything here by 5. So 5t squared is just t. -25t is going to be just -5 times t. And -30 divided by 5 is just going to be -6. So here's our quadratic. That's what we have to solve for t in. T squared is minus -5t minus 6 is equal to 0. Okay, you can actually factorize this one, but I'm going to show you how to make use of the quadratic formula. When your motion is not symmetric, okay, then you're always going to get a quadratic where you have to use the quadratic equation. When your motion is symmetric, like it was up here, okay, look at what happened to our quadratic. There it is. But look at what it reduced to. It reduced to something like that, which is very simple to solve. It still has 2 solutions, so be careful. Okay, you might still make a mistake, but there you don't. It's very easy to solve. So whenever you have a symmetric situation, the quadratic here reduces to something which is trivially solved. Whenever you have a non-symmetrical situation here, like this, an asymmetrical situation, okay, and why is it asymmetrical? Because this leg of the motion on the way down is different than on the way up. Okay, so that's not symmetrical. You're going to wind up with a quadratic equation like this, which you have to make use of the quadratic equation to get the 2 times. Okay, now you should know this from your high school math. Whenever you have an equation, this is probably the way you learned it in high school. Whenever you have a quadratic of the form ax squared plus bx plus c is equal to 0, that is solved. X is solved by minus b plus or minus, there are 2 solutions, one for the plus, one for the minus. Plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so you need to know this formula, and you've probably seen it before. But you remember how a second ago I divided through by the 5 so that the coefficient of the t squared is 1? That makes life a little bit easier because a in here, the capital A, is always 1 in the way I do it. All right, so once you get it down to like t squared minus the rest of it, your a in this formula here, your capital A, is 1. Your capital B is -5. All right. And your C is -6. You got to be careful here, and hopefully you've done a lot of these problems in the past. If it's -5t squared, then B is the entire coefficient, including the sign. So it's -5, okay? And the C here is the entire constant term, including the sign, so it's -6. All right, so once again, in this problem here, capital A is 1, capital B is -5, and capital C is -6, okay? And then you could substitute in. There's also one other thing you have to be careful. This is -b, and so you're going to wind up with -5. So you're going to have two negatives there, okay? So just be careful with that too. You'll see that in a second. So substituting into our quadratic formula, remember B was -5, so we had -b, so we have -5 there. Plus or minus, there are two solutions, one for the plus, one for the minus. Square root of b squared, -5 squared, minus 4 times a was 1, so I didn't even write it in there, and c was -6, okay? Divided by 2a, but a was 1, so it's just divided by 2. And so the rest of this is just some algebra. The -5 is just +5, plus or minus the square root of -5 squared is 25. -4 times -6 is plus 24, okay, divided by 2. And this is 5 plus or minus square root of 49 divided by 2. Square root of 49 is 7. So it's 5 plus or minus 7 divided by 2. And the way you work this out, there's two solutions packed into one. It's 5 plus 7 divided by 2. 5 plus 7 is 12 divided by 2. That's your one solution. And the other one is 5 minus 7 divided by 2. Okay, so 5 minus 7 is -2 divided by 2. And so you get an answer of either 6 seconds or -1 seconds. And those are the two answers that come out of this quadratic right here. Okay, so by the way, this quadratic is easy enough that if you guys are, good at factorizing quadratics, you can see that this immediately factorizes, okay? But I wanted to show you how to use the quadratic formula because not all of them will easily factorize, all right? So let's just pause for a second and see how we got here. Just summarize again. Looking at the situation here, we had initial final position, initial final velocity, and so on. We decided to use equation number 1 to find the time. That's a quadratic here. When we plugged in all the numbers and simplified, we found that we had a quadratic equation in time, which we could not easily solve the way we could before. So we made use of the quadratic formula, and we got two solutions, t equals 6 seconds and t equals -1 seconds. Okay, and whenever you get these two solutions, you have to stop and you have to think, what's the interpretation of the 6 seconds? What's the interpretation of the -1 second? It turns out that there's an interpretation to both of them. Okay, the answer that we want to the question is actually going to be 6 seconds, but the -1 has a physical interpretation as well. So let me take a look here and let me move my image up here. Okay, so here's the entire motion. We start at the top here, we go up, we get to the maximum height, we come back down, and we get to the bottom. Let's take a look at this trajectory and let's put some time labels on it. When are we right here when I first throw it up? Well, t equals 0 by definition. Okay, that's when the clock starts. We start our stopwatch at this point. When do we get to the maximum height? Well, we found out above that that's 2.5 seconds. So we get up here at 2.5 seconds. When do we get back to here? Back to when it passes me on the way down. Well, that was 5 seconds. We also found that above. And there's the symmetrical part of this. Okay, and then when do we get from there to the bottom? Well, then it's at 6 seconds. Okay, so now that kind of makes sense. Okay, if this 6 seconds had been less than 5 seconds, we know that we would have done something wrong. So here we are, 0, 2.5, 5, and then 6 seconds. Okay, so what's that -1 second? Well, see, the quadratic formula, that is equation number 1, it really doesn't know when things begin and when things end. It just says I'm a parabola. And so you know what? You can actually run the time backwards in that parabola. So imagine you had a movie where this thing goes up and comes down like that. Run the movie backwards in time. Well, if you run it backwards, well, then it goes up, 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 up. It comes to here to where it started. But keep running it backwards. It came from the bottom there like that. So remarkably, if the ball had come from the ground, it would have been down here at -1 second. It would have been at me at 0 seconds. It would have been up here at 2.5, there at 5 seconds, and then over here at 6 seconds. Okay, so yeah, that's not physically what happened, but there is kind of a meaning. Okay, if the motion had not started with me, but had started 1 second earlier, it would have actually started at the ground level here. Okay, now why the ground level? Because when I did my equation number 1, what did I put in for the final position? For the final position, I put 0, which is ground level. When is it at ground level? Well, it's at ground level at 6 seconds, and it's also at ground level if you extend the time backwards at -1 second. Okay, so there is a meaning to it, although that's not exactly physically what happened. There is kind of a meaning to that -1 second. You have to look at the problem and decide whether you want the positive or the negative time. Okay, now it's pretty easy that it's the positive time here, because if it was at me at 0 seconds, then it's going to be at a later time, at a positive time. But later on in the course, when we do two-dimensional projectile motion, you'll see that you'll get 2 positive times. And you'll go, well, which of the 2 positive times do I want? Well, when we get there, I'll give you that interpretation. But it's a quadratic again that you're solving. You'll get 2 equations. Both of them are going to be positive, and you'll go, which one do I want? And the answer you'll have to figure out by thinking intuitively about what's going on with the motion. Okay, one last thing, and then we're done. Let's just take a look at the times there. Remember that this maximum height was 61 meters, okay, from ground level. So the height of the building was 30 meters, and then it went up another 31 meters. Now this isn't to scale, so this, this looks a lot higher than that, so I didn't draw it to scale. But from the ground to the top of the building is 30 meters. From the top of the building to the maximum height is 31 meters. Let's take a look at how long it took the ball to go up and to come back down. It takes 2.5 seconds to go up 31 meters. It takes another 2.5 seconds to go down 31 meters. And then it only takes 1 second to travel 30 meters. And you go, why is that? Well, because in this portion of the motion, it wasn't moving that fast. But remember, this is accelerating, so it's going faster and faster and faster. So by the time the ball is here, it's going much faster than it was over here, up at the top. In fact, at the very top, it was at 0. So it's 2.5 seconds to travel the first 31 meters, but then it's only 1 second to travel that extra 30 meters until it hits the bottom, because it's traveling a lot faster. We'll take a look at the time between 0 and when it was, if you run the time backwards, when it was at ground level, it's -1 second. So between the 30-meter mark and the ground level is 1 second on both sides, whether you're talking on the negative side or the positive side. Okay, so 1 second in this portion of the projectile motion if you went backwards in time, and 1 second in this portion of the motion if you look at the positive time. Okay, so there you go. There, I'm just trying to point these things out to you. You don't need these intuitions to solve the problem, but the more intuition you have, the easier it is to solve the problem. And also, if you do make a little silly arithmetic error, the easier it is to catch it. Because if you see something that doesn't make sense, a number that doesn't make sense, you'll go, oh, I must have done something wrong. You'll redo it, and you go, oh, you know what, I forgot to square something, or I forgot that negative sign there. And that's how you avoid errors. Okay, you look at the final numbers and you see, do they make sense? And yeah, they make a lot of sense here. Okay, they make a lot of sense. Okay, like if we had found, like instead of 6 seconds, we had found 4 seconds, you go, wait a minute. If it's here at 0 seconds, it's there at 2.5 seconds, it's there at 5 seconds, how can it be at the ground at 4 seconds? There must have been something wrong. So, those are the kinds of things that you can catch. Okay, guys, that's the end of this lecture. Thank you very much.